So that cylindrical. Then finally we'll go to spherical. Spherical coordinate is against even a little bit more complication than the cylindrical one. Then we'll have we'll make one more step to make the argument, and then we'll introduce another. Actually, there's some other equations. Depends on the situation. You have the radial equation can be different. Now, one more thing I probably missed in the cylindrical coordinate is the L. When the situation L is 0, well, remember that L is with d squared z d c squared equals to L squared c squared, right? If L is 0, which means it doesn't depend on c, right? You get a problem that independent of z, which make the problem a 2D problem, two-dimensional problem. Only in it's just like the polar coordinate in 2D. So the solution, and then all the Bessel function in the row direction reduced to the power function, and that we have a home. I don't think we have homework, but the homework has a problem. It's not in the textbook problem. I have a homework problem for you. For 2D, yeah. So there's a form of the general solution for exactly this situation when L is 0. So you don't get Bessel function, you just get power law, R to a certain power. I think exactly R in this case rho to the m or rho to the minus m. And the cylindrical, the azimuthal part is the same. We still have sine or cosine m phi, or e to the I m phi. That part is the same. And you don't have c because it's independent of c. So you have the rho solution, power law, except that there's one special case that is for m equals 0. Then there's one extra solution other than just simply a constant. You have a log rho. It's also acceptable solution in 2D. So you have one more solution. So that would be a homework problem. And so sometimes there's a special cases you need to consider separately. So, for the special value of L equals 0, you get the form of the solution can change totally. Instead of a Bessel function, now you get power law, which is actually the limiting case. You choose all the Bessel function and take the limit of rho goes to L goes to 0, which is the argument, and argument goes to 0, and you recover the power solution. Okay, and so go to the spherical. Again, the same Helmholtz equation. So you just look up look up a table and for the Laplacian, the form of Laplacian, and the textbook write it in unnecessary complicated form. I mean, if you write it, usually the first term, the rho, the r, the radial coordinate should be r squared, and partial r squared. Sine partial r. That's the radial term. And some paper might list it in a different form. I don't think the textbook has both forms. Let's see, in the front or in the back. Is that one? Yeah. And it has this in curvilinear and the h1, h2, x3 for different coordinate system. But if you there's another form in the radial part that is also accepted. The two forms, when you work out the derivatives, they give you exactly the same second derivative and first derivative. So that doesn't matter. So, The theta part is 1 over r square sine theta, just sine theta. And then d theta. Sine theta point of so what's it theta? And then there's the azimuthal angle term, which actually exactly this like the cylindrical one, except it's right is r squared sine squared theta, which is what we in cylindrical coordinate, this is just what that's rho squared in the denominator. So it's exactly the same form. Also square sine, also phi square. I think that's it. And then plus k square. Right, and that's the form. And just let's consider one separable solution in the form of capital O, depends on little o, capital theta, depends on theta, and capital phi, depends on phi. Okay, and just follow the procedure, just substitute this into the equation and divide it by the same function. Then the first term gives you 1 over O r squared d O r squared d capital O d O. Right. And the second one gives you 1 over r squared sine theta after theta, but this is not theta, this is theta. d theta sine theta d theta. Right. And the last one is 1 over r squared sine squared theta phi squared phi squared. And then the constant term is just a constant. K squared is just a constant. Right. Now the complication is that now all 3 coordinates are mixed in the original sense, because they're all in the whole of the all terms, and then sine theta is in this term and also that term. But you need to do it step by step again. I think the easiest one to do is multiply by r squared sine squared theta, so that the rest would be this. If you multiply r squared sine, just cancel this factor in the denominator, so that the rest will be a function of phi, right? And then you can now treat it as constant. Okay, so to make it slightly less writing, so just treat it. So once multiplied by here, so that depends on theta, r squared sine squared theta. Multiply this, you cancel r squared of sine theta here, r squared of sine squared theta here, but this one would be just your constant or m squared. So this becomes m squared divided by r squared sine squared theta. Okay, this now we see this one. This is a constant, and the solution is now for the phi solution is just like what we did, either sine or cosine, or this im phi, right? Assuming is you are the integer. Yeah, minus epsilon. Yeah, minus m. Yeah. So this is minus m squared divided by this. All right. So now you consider this equation now. change that to a constant divided by r squared or sine squared theta. Now it's still coupled in the sense that you have a, now this is r squared, r only, and this is r squared is 1 of r squared, is m. And the next thing is you can do is to get rid of the r squared, because all three terms have r squared, so multiply by r squared throughout, and that this one will depends on theta, right? This one will depends on theta, and that one doesn't depend on theta. That one doesn't depend on theta. Now we might as well write it out because that's getting too complicated to do a shortcut. Let's just write it like combining this term to here, because this two term doesn't depend on theta, basically r squared, right? And the rest depends on this theta. You have sine theta, delta theta, dd theta, sine theta, d theta, d theta. And that this one, a minus m squared sine squared theta. Right, that becomes a 0. Right, and now this we separate. This is a function of r only, right? It's a function of r only, and this is a function of theta only, and you can set this to 0. Let's look at what the textbook talked about first. Why is there lambda in your textbook? Equate each side to be a constant lambda. Okay, call this lambda. Okay, this is well, one is lambda, the other is minus lambda. And I think this is called minus lambda. And this is called lambda. This is called, because they add up to the 0, this is lambda. This is minus lambda. Okay. This is wondering what the lambda can mean. All right, so you just write it out. So this is one differential equation. This is another differential equation. When you write it in the form that that would become, this would be your 9.77. I missed the out. I didn't copy the out. That one is your 9.78. Oh yeah, we multiply by r squared. Yeah, multiply by r squared. That is k squared. Yeah, the form. I mean, you write this out explicitly in the form of your textbook. This in this case, in your textbook, divided by r squared, so we get and multiply by r to the other side. Move everything to the one side. Combine to be this operator, r squared dr, and then plus we divided by r squared here, multiplied by capital R, and then minus this lambda, capital R divided by R squared. That equals 0. So that's a radial equation, right? And there's a choice of k squared. So far, we consider k squared just constant, but you can generalize that to a more general form. I think your textbook put in the form, so you can generalize it to other forms. So the exact equation for the radial equation can be more complicated than just this one. Right? If it is this one, with a positive k square, then the solution is what we call the spherical Bessel function. That we later on will cover all that. At least need a little transformation to transform that to the standard Bessel equation. But then the capital R is given by what we call the spherical Bessel function. But we don't have to consider that right now. And the theta equation, then to write in, which is, I mean, we can write it out. It's basically just multiply the capital theta to the other side and put everything together. Minus m squared. Capital theta, sine square theta, lambda, capital theta. Okay. And now this equation is, you put in another transformation, what we call the, change of variable, change the text will use t equals the cosine theta, cosine phi, cosine theta, yeah, cosine theta. Is that transformation? In many textbooks we use x, but just to avoid that the confusion with the Cartesian coordinate, I think your text will use t, but then it can confuse with the time variable t. But anyway, it doesn't matter; it's just a variable, and you can convert this all this derivative to ddt, and sine theta becomes sine square theta. This is a sine square. So the sine square theta is just 1 minus t squared. Right? And then the form is, that take a little bit of work to show, work out the derivative, but finally you will get this m. To keep this to the same, we work that out. Be 1 minus t squared, and dp t squared, p dt squared plus minus 2t, which is cosine theta. T is cosine theta, and t y has become p. Actually should be just theta. It's not, keeping on theta. Your textbook changed it to a value p. I don't know why. Yeah, because we usually call that Legendre polynomial or Legendre function. So that's called p. That actually doesn't matter because we are considering the theta solution now. Let's keep it the same, theta, capital theta. Right, the solution for this one is what we call the associated Legendre function, right? And there's one more complication is that whether your equation that depends on the value of t, whether you include t equals to plus or minus 1 or theta equals to 0 prime. Right? It's similar to what the phi situation, whether you include all theta or 2 pi. Now for theta, if you include, so this is theta, right? If you include 0 or this axis or pi, which is the lower z-axis. If the problem involves these two axes, then there's a restriction on the acceptable value of the, I think in this case would be your lambda. Say that again.
Are we differentiating?
Yeah, sorry. Copy wrong. This is a T equation. This is a theta. This is just transform this to this one. Do I have time here? No. I mean, if we have time, we can work out the derivative and show that they are the same. But it just takes some transformation to get to this, right? But before we do that, I just want to write down the solution. That the eigenvalues is fixed by this situation. If you included that, to include zero, theta include 0 and pi, then lambda is L times L plus 1. L is from 0. Right? You need to fix the value of that in order to have solution, right? Otherwise, the solution is singular at the boundary value. So if you include then the solution will be what we call PLM. Looking at your textbook in him, it didn't actually write it down. Yeah. In the equation 9.82. So the solution will be PLM. If you include that, you only have one solution, because the other solution, just like what in the Bessel equation situation, you just ignore the singular solution. Okay, this way that would be some constant times PLM cosine theta. That depends on T, which is cosine theta M. Right? For this, the solution for this one, right? Then these are called associated agenda function, right? And they are not polynomial, but for the special case for M equals 0, which is the case that this is 0, just basically this is just becomes just a constant. So you don't have both don't have phi dependencies. So the solution is independent of phi, or there's cylindrical symmetry. If you have cylindrical symmetry, then this PLM becomes what we call a agenda polynomial. Okay, and all this we'll talk about it in later chapters. So we have a chapter on agenda polynomial and associated agenda function. We have a chapter on Bessel function that will include a discussion of spherical Bessel function. So, we'll talk about all this. So right now, I just introduce all the possible equation and possible solution. So later on, we'll look at this equation a little bit details. Okay. So now this time your textbook write down the general equation, the 9.86 would be your general solution. Right? You have the spherical Bessel function multiplied by. Let's just copy it for you to see. It's this line. The general solution is just, this is 9.86. The sum over all the possible L and M. Now, assuming you include 0 and pi, so you restrict to this case, the lambda is L times L plus 1. The solution is associated agenda function. So you sum over L. L is from 0 to infinity. M is from minus infinity to infinity. Or integer. Okay, and now the radial part, after you put it in here, And for this ALM, you have the spherical Bessel function little j of order L. And that depends on KL. And then another one that also spherical Bessel function, but now it's Neumann, the Neumann part. Okay, so that's the radial part, and the theta part is PLM cosine theta. Okay, and then the azimuthal part, you can just write e to the IM. I mean, not using your textbook situation. You can just UM. Your textbook use cosine theta, cosine m theta, sine m theta. So that restrict m to positive integer. But if you use e to the IM phi, that's you can use this sum over all positive integer. Great, and it's okay. So that would be the general solution. And one more notation is sometimes people will combine these two factors with some normalization constant. That I mean, you can absorb the normalization into this coefficient, but then you can write this combined term to be what we call spherical harmonics, YLM. That depends on cosine, depends on theta and phi. Right? Dependency is just exactly this one, just this combination PLM times e to the IM phi, right? And multiplied by normalization constant. The good thing about the spherical harmonics is they are defined because the normalization constant is defined in the function. So they are defined as orthonormal. So, so they satisfy the orthonormal condition so that make it using spherical harmonics somewhat easier. Okay, and I guess that would be everything. That's a example, which is okay, except that you haven't learned enough about all this PLM or even the simpler version, the Legendre polynomial, which I think your example is just consider PL, right? And that make the discussion slightly, I mean, difficult because for at least for those of you that haven't learned the Legendre polynomial, then there's some property of the Legendre polynomial that you need to learn before we can do the expansion in Legendre polynomial. So that example, maybe we wait until we learn about Legendre polynomial before we come back to doing something similar. Okay, and so we skip that. Other complication is the form of this K. Again, like this form is with the spherical Bessel function. That because we have this K, we have the Helmholtz equation, and if it is a Laplace equation, we set K to 0. You can set K to 0. Then just like what we did with what we discussed in the two cylindrical coordinate, the Bessel function, you take the small argument limit, then it becomes power. And in the case of setting K to 0 or consider the Laplace equation, then the general solution are again the power law. That is instead of this one, you have R to the L or R to the minus L plus 1. In that case, let's just see. R to the L. Instead of these two J and Y, R to the minus L plus 1. Right. So that is you can go back to here. If you set this to 0, right, and set lambda to L times L plus 1, and set K to 0, you can work out the two solutions, or you can just substitute this to form of R to this power into here to see if you get the same. I mean, if you satisfy the equation, say if R, the capital R proportional R to the L, that this will give you, then keep working out this one will give you L DDR R square L times R to the L minus 1, right? So the first derivative will give you this one. And then multiplied by R squared becomes changed to L plus 1, right? You have L. Another derivative will give you L plus 1 factor. And then R to the L plus 1 minus 1 with R to the L, right? And then divided by 2, R to the L minus 2, right? And now this time L times L plus 1. This is R to the L, and divided by R squared with R to the L minus 2. And this is a negative sign, so the two terms cancel, right? So you can check that this is a solution. And similarly, you can check that this one is also a solution. Okay, so that for the past equation, you get, instead of spherical vector function, you get this just simple power law solution. And that's another remark. And then for quantum mechanics application, that K, if you use the generalized form of K instead of a constant K, depends on the functional form. You can either get the Lacouri differential equation or the Hermite equation. So the first case, you get the Lacouri polynomial. The second case, you get the Hermite polynomial. And I don't know whether in quantum mechanics you will see that, but that's also coming from the same consideration, except now it's just not a constant K square, but it depends on the potential, whether you have the first K, I think, is from the atomic, just Coulomb potential. The second case is for a simple harmonic oscillator. And you get the different solution. So the idea is that this form of the equation change when you choose different K. For constant K, non-zero K, you get all this spherical vector function. 0, K equals 0, you get power law. And then the functional form depends on the form of K squared, you get other solution. The equation change and the solution change. Okay, but then the YLM part is still the same. The spherical part is still the same. So the YLM is also, the spherical harmonic also applied to quantum mechanics calculation. Okay.